Artificial transmutation occurs when a stable nucleus is forced to decay into a new element by being bombarded or shot at the high-speed particle. So they're different from your natural transmutations because a natural transmutation is one that occurs naturally, occurs spontaneously. So an unstable nucleus will spontaneously emit or release some sort of particle. So for those reaction equations, we saw that there would be one reactant in that equation. However, for artificial transmutation, since it's done by man, we'll have two reactants in the equation, one being the nucleus and the other one being some sort of particle. So artificial transmutation reactions are used for many different reasons, but a lot of times, sometimes these cyclotrons or synchrotrons would be used in order to speed up these charged particles super fast so that they are then able to have enough energy to bang into that nucleus and then produce some new element. So these artificial transmutation reactions can be used by scientists with different kinds of these particle accelerators to create these artificial elements, things like plutonium or oganesson. These elements would not naturally exist on Earth, however, they are able to create them or artificially make them using this artificial transmutation. These reactions are also used to bombard stable elements inside some sort of cyclotron to manufacture some short-lived radio tracers for hospitals. So this is things like fluorine-18 can be used in PET scans to detect certain kinds of cancers. So there are two kinds of particles that could be shot at a nucleus. So the first one is a charged particle. So these would be like your protons or your alpha particles. So that's when those are collided with some sort of stable nucleus. This process would require a particle accelerator, and this is because those particles that are charged need to be accelerated to really extreme speeds to be able to overcome the repulsion that would occur between that bombarding particle and the nucleus. So notice how we have two reactants now. So anytime you see two reactants, an atom and a particle, that means it's a artificial transmutation. The other kind of particle that can be used in artificial transmutation is something that is uncharged, like a neutron. This is when a neutron is collided with the stable nucleus. Now, these do not need a particle accelerator because these particles, like the neutrons, are neutral. There's not going to be any of that repulsion, so it doesn't need as much of high speeds. So you've probably heard of Einstein's equation E equals mc squared before, and this is where energy equals mass times the speed of light squared. What this equation means is that mass and energy are basically two sides of the same coin. So sometimes we think of them as two distinct things, but Einstein says that they can actually convert back from one to another. In terms of nuclear energy and nuclear reactions, producing nuclear energy, there's something called mass defect that will occur. So we start out with a certain amount of mass, our atoms, but then as a result of our transmutation reaction, some of that mass is going to be lost because it's going to then convert into a large amount of energy. Mass defect just means that when nuclear energy is produced using these transmutation reactions, a small amount of mass can be converted to large amounts of energy. So now for our two main types of nuclear reactions, which are fission and fusion. Fission means to split, okay? So remember, fission is division. So this is where a heavy nucleus is split into two lighter. Over here we have this neutron and it's bombarding a uranium-235 atom. And as a result, fission is gonna occur. So uranium-235 is atomic number 92. Okay, it's very heavy. Fission is going to split that heavy nucleus into things that are smaller. So here we can see that barium element 56 is created, and then also krypton element 36. Fission is division. Heavy nuclei split up into lighter nuclei. Fission is used all the time, all over the world. For one, it drives commercial nuclear power plants, which provides about 10% of the world's electricity, and it does this without emitting any harmful greenhouse gases into our atmosphere. So by bombarding uranium-235, or sometimes it can be plutonium-239 with neutrons, we trigger a controlled chain reaction that generates an immense amount of heat to produce electricity. In its uncontrolled form, this exact same process occurs in our atomic weapons. The bomb that the US dropped on Nagasaki and then also on Hiroshima were both fission reaction nuclear bombs. So this is more of an uncontrolled form. It would cause this chain reaction of transmutations of heavy nuclei to lighter nuclei, causing a really, really, really large amount of energy to be released and can cause a lot of damage. The second type of nuclear reaction is fusion reactions. So fusion means to fuse or to join. So this is when light nuclei, so things that are lighter, are joined or fused together to generate some heavier element, along with the release of large amounts of energy, of course. Fusion is a process that essentially powers the universe. So it's the engine of our sun, where extreme heat and pressure force hydrogen atoms to fuse into helium, releasing the light and warmth that sustains us here on Earth. So humans have only successfully done fusion on Earth in the form of hydrogen bombs. There was one that was dropped as a test over the Pacific Ocean. It was never actually used in war, but it is roughly 700 times more powerful than the plutonium bombs that were dropped on Nagasaki. So they're way more powerful. These fusion reactions generate a lot more energy than your fission reactions. So scientists are actively building experimental reactors to harness controlled fusion. And this is to unlock a source of clean and unlimited energy without the risk of catastrophic nuclear meltdowns that often occur with our fission nuclear reactors. So this is just an overview between the two types of nuclear reactions again. So we have our fission and our fusion. Fission is division. So we have something that is heavier, an atom that is heavier or larger is going to divide into two nuclei that are lighter and always emitting large amounts of energy. And then we also have fusion, where we have two light nuclei that are fused or joined together to create something that is heavier. Okay, both of these are going to have that mass defect, where small amounts of mass are going to convert to large amounts of energy. Okay, so whether it be fission or fusion, they're both going to release a lot of energy. However, even fusion reactions are known to be 700 times more powerful than fission. Okay, so fission is like what is occurring in our nuclear reactors that are generating 10% of the world's electricity. Also used in many of the bombs that were dropped during World War II. Okay, however, our fusion reactions are the reactions that occur on the sun and how we get our heat and our light that sustains life on Earth. Hydrogen bombs are an example of a fusion reaction, which never actually has been used in war, has only been a test. But again, it generates a large amount of energy.